Let's be clear, this Eeprom programmer is designed to program 25 series Eeproms that run at 3.3 volts over an SPI data bus and 24 series Eeproms that run at 3.3 volts over an I2C data bus. That's its design limitations, nothing else. If you need to program or read an Eeprom, you must first identify what that Eeprom is and then select the appropriate Eeprom programmer, as this one in many cases is not suitable. Even with the 24 and 25 series, you're going to need a range of clips and connectors to couple up to this device. And the first part of this video deals with how I overcame a particular problem I had. The second part of this video deals with an issue with the logic levels coming out of this UART to the Eeprom. I look at the specifications in some detail and demonstrate a modification that would suit. However, in practice, I have programmed a fair few Eeproms with this device in its standard form, and I've had absolutely no problems, so it is debatable whether any modification is necessary or not. However, it does leave me with a niggling doubt, and one that I'm aware of, and I think that being aware of it is better than not knowing. This is an Eeprom, and when designing circuits, it's quite common practice nowadays to put in a connector on the board or some pinouts so that you can remotely access these devices and program them and reprogram at will. Now, I omitted to do that, so I was left with the option of having to pre-program these using this little header board, which I had to solder the component onto and then program it onto using an SPI programmer. So once assembled, this unit fitted on there like so. Then I'm faced with unsoldering this and then soldering it into position on a PCB. According to the data sheet, this is a WSON 6 by 5mm SP package. Now, it's available in different sort of packages, but this is the one I've got. I looked around and I found a connector for them, and it was about £15 and it was on the other side of the world. And as I didn't have time to wait, I decided to make my own connector. And this is what I came up with. I 3D printed this little thing, and the package sits inside, like so. I'll show you a little bit more of a close-up of this. I pushed the wires that form the pins that touch the bottom of the device are inside here. Now, you're not getting a very close look at this. Let me see if I can do it a bit closer for you. Perhaps you can just see them. Now, this is 0.4mm wire, and it fits in the little holes like so. It pushes all the way through, or should do. It's typical, isn't it? When you try to demonstrate something, you can't do it Let me try another hole. I can barely see the holes myself. Now, pushes through. The one at the back goes off to the header PCB, and this one that's bent over forms the connector. I hope you can see that. Now, if we put this back in here, and put this back in here like so, come out a bit. We need some way of clamping it in there. I came up with this idea, which was nothing more than a long bolt with a screw on, nuts. This little pad goes over the IC to protect it from the screw, like so. This clips over the integrated circuit, assembly, up it comes. And as per usual, in practice, when you're not looking over a camera, it's a lot easier. It goes in, up, over, tightens down. And one just does it up quite loosely, and when it's plugged in and everything's up and running, if it's not detected, you just give it a little bit more of a twist. If it's not detected, a little bit more of a twist. Never ever use any sort of pliers or a spanner or Allen key to tighten this thing up, otherwise you could damage things for yourself. The final version came out like so. It plugs into the board and does that. Naturally, that just left me then with one stage of soldering. So I've dispensed with 2 stages of soldering. However, still had to solder, which was tiresome. I redesigned the PCB, circumnavigated all of that, such that I now use, if I have to, a cable from the programmer to the board, and hence this is sort of redundant. Now, I drew this up using FreeCAD. I sliced it using Cura on its superfine settings, and I have just a completely bog standard 3D printer, which is an Ender 3, and I was absolutely surprised that I could print and get such small little holes in to make a viable device. That was a bit surprising. However, it is difficult. I'd like to have put it on to Thingiverse, but I think that a lot more of you will have a lot more trouble with this. It's not don't always get a successful print, so I'd probably get slated for it. If there's any interest, just let me know. I'm going to go on and talk about programming Eeproms. Most of you want to program an Eeprom because you're probably hacking your BIOS or EFI in your laptop because you forgot your password. Now, it's no point going, oh, what do you do if you've got a so-and-so laptop? What do you do if you've got this laptop or that laptop? It's absolutely pointless. What you need to know is what Eeprom you are programming. And once you know what Eeprom you have, get the datasheet for it. Study the datasheet, learn how it works and functions, and then you'll be in a better position to understand the next stage of your process. Now, a lot of videos I've seen people unsoldering these things out of laptops. Don't be fooled. This is not a sort of a sensible thing to do. You could do more harm than damage if you haven't got necessary soldering skills, like most of us haven't. And it's more common now to couple across using a cable. Now, some of these package designs of Eeproms, you can see the pins on the side, and you can get clips that go onto the outside of the package, and via a cable go to your Eeprom programmer. However, if you're faced with this sort of chip, do look around the board. There will be some way of accessing the chip on the board. It was just pure stupidity not to have some access point to program these things. And I do know that the most versions of things like MacBook Pros that use similar chips do have a cable access point. Now, having said that, this programmer is an SPI programmer. This is an SPI chip. Now, once you've identified your chip, you may find that it's not an SPI chip, and therefore this will not work, or is not suitable in its current form. Enough said about that, and I have no qualms about programming an Eeprom with one of these straight by plugging it in. However, when it comes to cabling from this to another device, I do have some reservations, and I will cover that now. And we're going to look at the datasheet for the Eeprom. We're going to look at the datasheet for the UART that they use here, and we're also going to look at a circuit diagram for this board. We need a schematic drawing for the CH341A. Schematic. And I've done at one transistor down here. It's an excellent article to read, and it does go in about the logic levels coming out of the CH341A. And I would read it if I was you. And we're going to take a close look at the view image. And the first thing that strikes you about the Eeprom programmer is that the chip is running at 5 volts, whilst we're programming Eeproms that are running at 3.3 volts. That begs the question that the data out and the clock out signal levels feeding this chip are going to be rather on the high side. Now, I'm quite happy to stick in an Eeprom in here and program it and take my chances. However, when it comes to programming something via a cable to an external device such as a laptop, you've got to remember you are coupling up to an SPI data bus, and there'll be other components that are daisy chained along there, and it does rather beg the question, are they resilient enough to put up with the slightly higher voltages? And I will cover that point later. It's rather odd that they chose to do it this way, because this device itself is capable of running on 3.3 volts. and if you read the data specifications. Although one mod would be to take the data out and the clock out and put them through logic level converters to bring our signals to the right specification for feeding into the Eeprom. I feel that would be unnecessary if they had to run this at 3.3 volts. Now, the output from this regulator could have been diverted off and this wired up accordingly, but perhaps this is just on the small side, and there wouldn't have been enough power to run this chip. I don't really know, and it's worth speculating, but personally speaking, if I was just programming 3.3 volt Eeproms, I would want this running at 3.3 volts, and I think it's perhaps worthwhile giving that a go at some time in the future. Now we'll pop over to the datasheet for CH341A and I'll show you exactly what it says. I'm now going to look for a data sheet for the CH341A. This is specifically for the chip that they use in the programmer. Now, don't click on any of the ads, come down here, and I don't fancy the look of this one. I'm going to look at this one and see what... No, this one. I'll try this one, I think. Yeah. Well, sometimes it can be a bit hit and miss. Let's look until we find one. Oh, the first one I should have chosen. There you go. What an idiot. If you're interested in modifying a CH341A programmer, then this would be essential reading, and I have lots of information in there that you probably need. Now we're going to look at the pinouts while I explain how this can work on the 3.3 volts. Here you can see that pin 28 and pin 9 are the key power rails, and it says here for VCC on pin 28, positive power input port requires 0.1 microfarad power decoupling capacitance. So it's got to be coupled up to 5 volts and with a decoupling capacitor down the ground of 0.1 microfarad. Pin 9, however, attachment of VCC input external power valve 3.3 volts connects of 0.01 microfarad decoupling capacitor outside valve 5 volts. Well, it sounds a bit clumsy, and I presume that the initial specification was written in some other language and has been translated. Broadly speaking, it says if you've coupled up to the 5 volt rail, you need to decouple pin 9 via a 0.01 microfarad capacitor. However, we need to know how to run it on 3.3 volts. There is some more information, and I'll show you that now. Well, here we are on another part of the data sheet, and it says the CH341A supports 5 volts and 3.3 volts source voltage. When working on 5 volt source, etc., we've already covered that point in the decoupling capacitance. If the work power is 3.3 volts, that's going to sound a little bit odd, you connect V3 to VCC and keep VCC at 3 volts, 3.3 volts. The voltage of the other circuit, which is connected to CH341, is no past than 3.3 volts. I think that means you mustn't put any more than 3.3 volts on pin 28, which is the VCC, if you've got it wired like this. So you take pin, I think it's pin 9 to pin 28, and put 3.3 volts on there, and you have your device working at 3.3 volts. There is another mention somewhere in the specification. Let me find that. I think this shows it more clearly about what's going on, and it says V3 doesn't connect to VCC. Then the voltage that you can apply there is 4.5 to 5 volts with a 5.3 volt maximum. And if V3 is connected to VCC, then you can only apply 3.3 volts with a maximum of 3.6 volts. I think that's quite clear, and such that I think it would be worth trying that and seeing what happens, rather than putting in logic converters to sort of bring the data out and clock to the appropriate levels. I have no idea whether it would work though. Now, while this fuss, well, let's go and find a data sheet for the Eeprom under consideration. Let's type in the name of our chip. W25Q64FV Datasheet. Yeah. Come down here to this one. Did we have a PDF for this particular one? I want to go down and look for its electrical characteristics, which we'll find in section 7. Absolute maximum rating 7.1, page 71. Seems to work. These are the electrical characteristics, the absolute maximum ratings. The supply voltage can withstand voltages of as low as minus 0.6 being applied to it, and no greater than 4.6 volts. This is not the operating range of it. These are the sustainable voltages that it can take before the chip is damaged. Now, if we look at the voltage applied to any pin, it says minus 0.6 to VCC plus 0.4. So when it comes to the chip pins for the data in and clock coming from the CH341A, I could imagine somebody saying, oh, 0.4 and 4.6, oh yes, it'll take a 5 volts, okay. Well, I think more by luck than judgment. I think it's been operated well without outside of its design parameters, but we could argue about that, and I haven't got the appropriate test gear to establish that at all. What we're seeing is the 5 volt rail. It's 1 volt per division. That's ground. 1, 2, 3, 4, 5. There we go. We've got this noise on the 5 volt rail, which is almost sort of about 0.7 volts peak to peak. Now, I think that noise is coming from the onboard crystal oscillator. And you can see a good reason for making sure you've got decoupling capacitors in. I think, and only think, that it could be a product of dangling wires on with the scope lead and everything that may be increasing the pickup. I'll change it over to the ground so that you can see what the ground looks like. And this is the ground level. Basically speaking, the scope probe is connected to ground on the CH341A, and as you can see it's on no ripple on there. This is the clock output, the CH341A with the Eeprom connected, and it's quiescent state high, and it's 4 volts. 1, 2, 3, 4. Ground being there, and 1 volt per division. I find that a little bit odd. We're now looking at the clock output from the CH341A as it's programming the chip, and as you can see it's from 0, so that's 1, 2, 3, 4, up at 5 volts. And we've got a big overshoot on the front, which may be more to do with the scope probe than anything else. But we can got this ringing that we can see, which is, as I said before, I think due to the onboard crystal oscillator. Currently we're coupled up to the clock output from the CH341A on a modified device, and the clock output is sitting at 1, 2, 3 and a bit, about 3.3 volts with no ripple. Getting ready to program. We should see the clock signal appear. Again we've got the ripple top and bottom, which I believe is due to the onboard crystal oscillator. The level is about 1, 2, 3.5 divisions, in the order of what we would expect for a 3.3 volts working. The ripple has a period of about 20 nanoseconds, which makes it around about 50 megahertz. I couldn't be certain it wasn't coming from my computer, so I switched that off and unplugged it. Unplugged the device and powered it separately by using a battery. When connected to the battery, the ripple appeared again on the 5 volt rail. Disconnecting from the battery, the ripple disappeared. Connect back to the battery, ripple appeared, from which I presume it wasn't my oscilloscope that was oscillating. Personally speaking, I find the ripple too much. It doesn't affect the overall performance though. Had I been designing a circuit and something like this had occurred, I wouldn't have been satisfied. That's all I've got to say on the subject. I modified the CH341A to run on 3.3 volts by lifting pin 28, cross-coupling the wire to pin 9, and then taking pin 9 via this wire to 3.3 volts on the side pins here. On reflection, I should have picked up the 3.3 volts from the 3.3 volt regulator and just run it straight across. It would have kept the wiring down to a minimum, and hence any sort of pickup and interference would have been minimised. Well, what do I think about this device? Well, bearing in mind that in its basic state it's sold as a 3.3 volt SPI programmer, and as such, if your chips fall into that category, then it will probably do the job adequately. As you know by now, I have reservations about the powering of this device, and I've modified it to run on 3.3 volts, which seems sensible to me. Although I will say that I've had absolutely no problems running it in its standard mode. Is it worth bothering about tinkering around with modifications? No. It's cheap, it's a one-trick pony, without modifying, and modifications to this are going to be a bit brutal, and if you haven't got the necessary soldering skills, you're going to ruin it.